In the last lecture, I have introduced the theory, or you can say the concept of testing of hypothesis based on a heuristic consideration called likelihood ratio tests. The idea was that we should consider that possibility or those that hypothesis to be more probable that gives a higher value of the maximum likelihood. Based on that, I derived the likelihood ratio test for parameters of a normal distribution. I was considering the testing for the mean, and we had seen actually that the tests are almost same as the tests of derived using Neyman Pearson theory. For the variance testing, I derived a test for one sided null and one sided alternative hypothesis. Let me also consider for H 4, that is sigma square is equal to sigma naught square against K 4 sigma square is not equal to sigma naught square. So, I do not have to derive L hat omega, this is derived earlier, that is 1 by 2 pi sigma omega head square to the power n by 2 e to the power minus n by 2, where sigma omega head square is equal to 1 by n sigma x I minus x bar square. Now, when we are considering omega h, then mu head omega h remains same. However, sigma omega h head square, that is actually equal to sigma naught square, because only this is a point null hypothesis. So, at this point only one value will come. Your omega h is actually mu sigma square, mu is real and sigma square is equal to sigma naught square here. So, L head omega h, then this will be equal to 1 by 2 pi sigma naught square to the power n by 2 e to the power minus 1 by 2 sigma naught square and n sigma omega head square. So, if I take the ratio, the likelihood ratio is lambda x, that is equal to L head omega h by L head omega. I can write it as same thing, that is y to the power n by 2 e to the power n by 2 into 1 minus y, where y is equal to sigma omega head square by sigma naught square. So, we have seen the behavior of this function, this is equal to say g y. However, in the previous case y was always less than 1, but here y can take any value, and therefore, we need to look at the proper full behavior, that is g prime y is actually equal to n by 2 y to the power n by 2 minus 1 e to the power n by 2 into 1 minus y into 1 minus y. So, obviously, this is less than 0 if y is less than 1, it is greater than 0 if y is greater than 1. So, g y attains maximum at y is equal to 1, and the behavior actually we can also see what is g prime y, g double prime y. G double prime y is n by 2 y to the power n by 2 minus 2 e to the power n by 2 1 minus y n by 2 1 minus y square minus 1, that is greater than 0 if y is less than root 2 by n minus 1, it is less than 0 for y greater than root 2 by n plus 1. So, it is actually, that is g y is convex in this region, and in this region g y is concave. So, the shape is something like this, this is 1. Okay. So, the region T is to reject H 4 if lambda x is less than c. Now, lambda x I have written as g y. Now, g y less than c and g is a function of this nature. So, now you see here. So, suppose this is the point C and this is the curve g y against y here. So, this could be some value say C 1, this is some value C 2. So, if I say g y is less than C, this is equivalent to y being less than C 1 or y being greater than C 2. So, the region g y less than c is equivalent to y less than c 1 or y greater than c 2. So, y is defined as, so we can say reject H 4 if sigma x I minus x bar whole square by sigma naught square is less than say C 1 or sigma x I minus x bar whole square by sigma naught square is greater than C 2. And probability of sigma x I minus x naught x bar whole square by sigma naught square between C 1 and C 2 should be equal to 1 minus alpha when sigma naught square is the true value. Now, sigma x I minus x bar whole square by sigma naught square follows chi-square distribution on n minus 1 degrees of freedom. So, these are to be determined from tables of chi-square n minus 1 distribution. As a convention, one can take C 2 is equal to chi-square n minus 1 alpha by 2 and C 1 as chi-square n minus 1 minus alpha by 2, because the probability of between this, suppose this is alpha by 2 probability, this is alpha by 2 probability, then this is 1 minus alpha. So, this is C 1 star, this is C 2 star that we can take here. You can see that the form is similar to the test which is derived in the UMP unbiased test, except that in the UMP unbiased test we got two conditions there. One of the conditions is the same, but one more condition was there. Here we are getting only one condition. So, there is a similarity here, and in fact, one solution corresponds to that. Before we move to two sample problems, let me give an application to the distributions either which are discrete or which are not in the exponential family. So, let us consider likelihood ratio test for a binomial proportion. So, we have the data x following normal binomial NP distribution, and we are considering the hypothesis testing problem, say p is less than or equal to p naught against say p is greater than p naught. Let me write it as h k, h 1 k 1 following our usual convention for one sided testing problem, h 1 and this is k 1. Now, your full parameter space is the interval 0 to 1 and omega h is 0 to p naught. Now, let us write down the likelihood function. So, L p x, that is the n c x p to the power x 1 minus p to the power n minus x. We have actually discussed in detail the maximum likelihood estimator for this problem. So, derivative and putting equal to 0, all those things are the standard. However, when we consider the parameter space under the null hypothesis, then we have to see carefully. So, I will write down the expression for that part. So, log of the likelihood is log of n c x plus x log of p plus n minus x log of 1 minus p. So, let me write it as small l. So, d l by d p, that is equal to x by p minus n minus x by 1 minus p, that is equal to x minus n p divided by p into 1 minus p. This is less than 0 if p is greater than x by n, and it is greater than 0 if p is less than x by n. So, if we look at the behavior of L p, this side we are having L p. So, up to x by n, this is increasing and thereafter it is decreasing. So, p hat omega is equal to actually x by n, and therefore, the L hat omega, that is equal to n c x x by n to the power x 1 minus p to the power 1 minus x by n to the power n minus x. Now, on omega h, you are having p less than or equal to p naught. If I have that, then there will be two cases. I may have p naught here and I may have p naught here. So, if x by n is less than or equal to p naught, then p hat omega h, that is equal to x by n. However, if x by n is greater than p naught, in that case, if this is p naught, then the maximum value is attained at p naught, because this is outside the region. So, then p hat omega h is actually equal to p naught. That means, we can say p hat omega h is actually equal to minimum of p naught and x by n. So, L hat omega h is equal to n c x p hat. So, x by n to the power x 1 minus x by n to the power n minus x, if x by n is less than or equal to p naught, and it is equal to n c x p naught to the power x 1 minus p naught to the power n minus x, if x by n is greater than p naught. So, if you compare L hat omega and L hat omega h, then for the case x by n less than or equal to p naught, they are the same. In that case, you always accept, because both are the same. So, you accept h 1. So, L lambda x, that is L hat omega h by L hat omega, that is equal to 1 if x by n is less than or equal to p naught. So, always accept h 1. Now, when x by n is greater than p naught, in that case, this lambda x, that will become equal to p naught to the power x 1 minus p naught to the power n minus x divided by x by n to the power x 1 minus x by n to the power n minus x. So, if I look at say lambda star, that is equal to log of lambda x, that is equal to x log of p naught plus n minus x log of 1 minus p naught minus x log x by n minus n minus x log of 1 minus x by n. So, what is the behavior of this? Because LRT is reject H 1 if lambda x is less than c. Okay. Now, if I write that in terms of x, what happens? So, we need to analyze the behavior of this. If I consider the derivative of this with respect to x, I get log of p naught minus log of 1 minus p naught minus log of x by n minus x n by x 1 by n plus log of 1 minus x by n plus n minus x by n minus x n 1 by n. So, you can see this term gets cancelled out and this whole thing cancels out. So, we are getting log of n minus x p naught divided by x into 1 minus p naught. Now, we have chosen that x by n is less than or equal to p naught. This implies x is less than or equal to n p naught and n minus x will be n minus x will be greater than or equal to n into 1 minus p naught. So, d by dx lambda star x, this will be less than 0. Sorry, this is greater actually. I made a mistake here. X by n is greater than p naught region we are considering. So, x is greater than n p naught, n minus x is less than n into 1 minus p naught. So, what will happen that if we consider this term log of n minus x p naught divided by x into 1 minus p naught, this term becomes less than 1, therefore, log of this becomes less than 0. So, this is less than 0 for x by n greater than p naught. That is lambda star is a decreasing function of x, that is lambda x is a decreasing function of x. So, note here I am considering the likelihood ratio, that is lambda x, the region is lambda x less than c. Now, lambda is turning out to be a decreasing function of x. Therefore, this region is equivalent to, therefore, the likelihood ratio test for H 1 versus K 1 can be written as reject H 1 if x is greater than some C 1. Now, C 1 is to be determined from the size condition, that is probability of x greater than C 1 for p supremum of p less than or equal to p naught. This should be equal to alpha. Now, as a function of p, what is this term? This is actually sigma n c x p to the power x into 1 minus p to the power n minus x, x is greater than C 1. If you plot the binomial probabilities, the behavior is like this. Now, we are looking at the right tail. Now, right tail corresponds to higher number of successes. So, this probability that is the right tail of the binomial distribution corresponds to the higher number of successes. So, it is increasing in P. So, supremum is attained at P equal to P naught. So, C 1 is determined from probability x greater than C 1 equal to alpha for P is equal to P naught, where x follows binomial n P naught. That means, you have to see the tables of binomial probabilities. Now, this being a discrete distribution, it is quite possible that there may not be any C 1 for which this is equal to alpha. It may be that no value of C 1 gives an exact alpha. So, we may choose C 1 such that probability x greater than C 1 at P naught is less than or equal to alpha, but probability of x greater than C 1 minus 1 at P naught is greater than alpha. So, this is the likelihood ratio test for the proportion of a binomial distribution. In the same way, suppose I ask for H 4 hypothesis, that is, if I consider P is equal to P naught against P is not equal to P naught. In place of P less than or equal to P naught, if I modify that, then we can, this region will not come, only this portion will come, and we will analyze the behavior of this function in a more appropriate fashion, because there will be two regions. One will be corresponding to x by n greater than P naught. We have already seen that in this region we are getting the function to be a decreasing function. However, if I consider x by n less than or equal to P naught, this value will become positive, and therefore, lambda star x will become an increasing function. So, let me just give the complete analysis for the two sided testing problem. If we consider the two sided alternative, that is H 4 P is equal to P naught against K 4 P is not equal to P naught. In that case, lambda x, that is equal to simply P naught to the power x 1 minus P naught to the power n minus x divided by x by n to the power x 1 minus x by n to the power n minus x. So, lambda the behavior of lambda star, we have seen that derivative of d by dx of lambda star x, that is equal to log of n minus x into P naught divided by x into 1 minus P naught. So, this is less than 0 for x by n greater than p naught and it is greater than 0 for x by n less than p naught. So, the nature of the function is then that it is increasing and then for x by n less than p naught it is increasing. So, if I am treating it as a function of x, then it is firstly for x by n, it is increasing and then it is decreasing. On this side I have x, on this side I have lambda x or lambda star x. So, now the region lambda x less than or equal to c, that is equal to these two regions. So, lambda x less than c is equivalent to x less than c 1 or x is greater than c 2, and we should have probability of c 1 less than or equal to x less than or equal to c 2 is equal to 1 minus alpha, where x follows binomial n p naught. So, this c 1 and c 2 can be determined from the tables of binomial distribution. I have shown you that even in the case of discrete case, the likelihood ratio test can give a nice and elegant solution. However, if the distribution is not in an exponential family, let us consider one example. Let x 1, x 2, x n be a random sample from an exponential population with location parameter. That is e to the power theta minus x is the density function. So, the likelihood ratio function is e to the power n theta minus sigma x I, which I can write as e to the power n theta minus x bar. This is for x 1 greater than theta, it is equal to 0 if x 1 is less than or equal to theta. So, naturally you can see that L is increasing in theta. So, theta hat is equal to x 1, this is over omega. So, L hat omega is nothing but e to the power n x 1 minus x bar. Let us consider omega h. For omega h, if I am considering, now this is an increasing function. In fact, you can see at theta is equal to x 1, this will be this value, but it is going like that. So, for omega h, theta hat omega h, that will be equal to x 1 if x 1 is less than or equal to theta naught, and it is equal to theta naught if x 1 is greater than theta naught. So, L hat omega h, that is equal to e to the power n x 1 minus x bar if x 1 is less than or equal to theta naught, it is equal to e to the power n theta naught minus x bar if x 1 is greater than theta naught. So, the ratio, that is L hat omega h by L hat omega, that is equal to 1 if x 1 is less than or equal to theta naught, and it is equal to e to the power n theta naught minus x 1 if x 1 is greater than theta naught. So, here in this case we will accept h 1, and in this particular case if I am considering e to the power n theta naught minus x 1 less than c, then this is equivalent to x 1 greater than c. So, this c will be determined from the size condition, probability of x 1 greater than c, when theta we are taking maximum for theta less than or equal to theta naught. This should be equal to alpha. Now, what is the distribution of x 1? That is equal to n e to the power n theta minus x for x greater than theta. So, if I consider probability of x 1 greater than c, that is equal to e to the power n theta minus c. So, this value is actually e to the power n theta minus c. So, if I take supremum theta less than or equal to theta naught, that is equal to e to the power n theta naught minus c, that is equal to alpha. That means, c is equal to theta naught minus log of alpha by n. So, the likelihood ratio test is, so when x 1 is greater than theta naught, reject h 1 if x 1 is greater than theta naught minus log of alpha by n. Now, we take up the likelihood ratio test for two sample problems. So, likelihood ratio test for two sample problems. To start with, I consider random samples from two normal populations. Let us consider independent random samples x 1, x 2, x m from normal mu 1 sigma 1 square, y 1, y 2, y n from normal mu 2 sigma 2 square. Let us consider the hypothesis, say, for testing of mu 1 less than or equal to mu 2 against, say, mu 1 greater than mu 2. We assume here that sigma 1 square is equal to sigma 2 square. In this case, we have derived the UMP unbiased tests. When this is not equal, that is sigma 1 square is not equal to sigma 2 square, it was known as a Variance Fisher situation. So, our parameter space is mu 1, mu 2 sigma square. Mu 1 is real, mu 2 is real, and sigma square is positive, and omega h, that is mu 1, mu 2 sigma square. Mu 1 is less than or equal to mu 2, and sigma square is greater than 0. Let us write down the likelihood function. The likelihood function is given by L mu 1, mu 2 sigma square x and y. So, that is equal to 1 by 2 pi sigma square to the power m plus n by 2 e to the power minus 1 by 2 sigma square sigma x I minus mu 1 square plus sigma y j minus mu 2 square. Log of L is equal to minus m plus n by 2 log of 2 pi minus m plus n by 2 log of sigma square minus 1 by 2 sigma square sigma x I minus mu 1 square plus sigma y j minus mu 2 square. So, if I consider the maximization over the full parameter space, so let me write this as small l. So, del L by del mu 1, that will give me sigma x I minus mu 1 by sigma square, that is n x bar minus mu 1 by sigma square. So, once again less than 0 if mu 1 is greater than x bar, it is greater than 0 if mu 1 is less than x bar. So, maximum is attained at x bar, that is mu 1 head omega is equal to x bar. Similarly, if I take del L by del mu 2, that is equal to n y bar minus mu 2 by sigma square, that is less than 0 if y bar is less than mu 2, it is greater than 0 if y bar is less than mu 2. So, maximum is attained at y bar, that is mu 2 omega head, that is equal to y bar. Let us also consider the maximization with respect to sigma square. So, we get minus m plus n by 2 sigma square plus 1 by 2 sigma to the power 4 sigma x I minus mu 1 square plus sigma y j minus mu 2 square. So, that is equal to, if I take m plus n by 2 sigma to the power 4 out, then I get 1 by m plus n sigma x I minus mu 1 square plus sigma y j minus mu 2 square minus sigma square. Once again, it is less than 0 if sigma square is greater than 1 by m plus n sigma x I minus mu 1 square plus sigma y j minus mu 2 square. It is greater than 0 if sigma square is less than 1 by m plus n sigma x I minus mu 1 square plus sigma y j minus mu 2 square. So, sigma omega head square, that is attained at this value where mu 1 and mu 2 are replaced by their respective maximum likelihood estimators. That means, it is attained at sigma x I minus x bar square plus sigma y j minus y bar square divided by m plus n. So, if we consider L head omega, so L head omega is equal to 1 by 2 pi sigma omega head square to the power m plus n by 2 e to the power minus m plus n by 2. Now, let us consider over omega h. Omega h. Over omega h, what is happening, that let us look at the derivatives here. The maximization were occurring at x bar and y bar for mu 1 and mu 2. Now, we are saying mu 1 is less than or equal to mu 2 over omega h. So, when x bar is less than or equal to y bar, we can treat them as such. So, when x bar is less than or equal to y bar, we take mu 1 omega h head is equal to x bar, mu 2 omega h head is equal to say y bar, and sigma omega h head square, that is equal to 1 by m plus n sigma x I minus x bar square plus sigma y j minus y bar square. There is no change. In this case, the ratio, that is L head omega h by L head omega, that is equal to 1. So, we always accept H 1. The hypothesis that I mentioned here, mu 1 less than or equal to mu 2 against mu 1 greater than mu 2. So, we always accept H. So, that is alpha is equal to 0. Now, the other possibility is when x bar is greater than y bar. Now, when x bar is greater than y bar, then we analyze. Firstly, you look at the behavior with respect to mu 1. Now, with respect to mu 1, you see it is initially increasing up to x bar and then decreasing. So, now if y bar is less than x bar, then we will have to modify this thing. What we do? Fix mu 2 first, say, okay, and then the maximum with respect to mu 1 is mu 1 head is equal to minimum of mu 2 and x bar. Now, if x bar is less than mu 2, then mu 2 head will be equal to maximum of x bar y bar, that is by finding the maximum with respect to mu 2, and we always accept H. However, another case occurs when if x bar is greater than mu 2. In this case, the d L by del mu 1, that is equal to m x bar minus mu 1 by sigma square. I think I wrote a little bit wrongly in the first place. This was m times, not n times. So, this one will become greater than 0 on omega h, because we are having mu 1 less than or equal to mu 2. Okay. So, with respect to mu 1, the maximum is attained at the line mu 1 is equal to mu 2. So, in this case, the log likelihood, that is L, I can write as minus m plus n by 2 log of 2 pi minus m plus n by 2 log of sigma square minus 1 by 2 sigma square sigma x I minus x bar square plus sigma y j minus y bar square minus m by 2 sigma square x bar minus mu 1 square mu square plus n by 2 sigma square y bar minus mu square. So, if I consider del L by del mu, then I will get mu head is equal to m x bar plus n y bar divided by m plus n, that is the grand mean, that is mu 1 omega h, mu 2 omega h, because I have assumed them to be equal here. And sigma omega h head square will also get, because there we were getting x I minus mu 1 and y j minus mu 2. So, this will become simply sigma x I minus x bar square plus sigma y j minus y bar square plus m n by m plus n x bar minus y bar square. So, L had omega h, that becomes equal to 1 by 2 pi sigma omega h square to the power m plus n by 2 e to the power minus m plus n by 2. Now, the rejection region is we reject h when lambda x, that is L hat omega h by L hat omega, that will become sigma omega head square by sigma omega h head square less than say some to the power n by 2 will come. So, I am to the power m plus n by 2 less than some c, or we can say sigma omega head square by sigma omega h head square is less than c 1. Now, we substitute the values here. This is sigma x I minus x bar square plus sigma y j minus y bar square divided by m plus n, and in the denominator then I have sigma x I minus x bar square plus sigma y j minus y bar square plus m n by m plus n x bar minus y bar square. This is less than c 1. You take the reciprocal and then subtract, then this will give us actually m n by m plus n x bar minus y bar square divided by sigma x I minus x bar square plus sigma y j minus y bar square greater than say some c 2. Note here that x bar is greater than y bar, x bar is greater than y bar. So, this means I can take the square root here m n by m plus n x bar minus y bar divided by s p greater than some c 3, where s p square is nothing but sigma x I minus x bar square plus sigma y j minus y bar square divided by m plus n minus 2. So, the condition that we will be getting here is probability of root m n by m plus n x bar minus y bar by s p is greater than c 3 when mu 1. So, this is for general mu 1 mu 2, we have to take the supremum when mu 1 is less than or equal to mu 2. This should be equal to alpha. Now, note here root m n by m plus n x bar minus y bar minus mu 1 minus mu 2 divided by s p. This will follow t distribution on m plus n minus 2 degrees of freedom. This part we have considered earlier in the sampling distributions in my lectures on probability, because you are having actually x bar following normal mu 1 sigma square by m, y bar follows normal mu 2 sigma square by n, then sigma x I minus x bar whole square by sigma square, that follows chi square distribution on m minus 1 degrees of freedom, sigma y j minus y bar square by sigma square follows chi square distribution on n minus 1 degrees of freedom, and these are all independent. So, x bar minus y bar minus mu 1 minus mu 2, then if I consider this will follow if I divide by sigma root 1 by m plus 1 by n, this will follow normal 0 1, and sigma x I minus x bar square plus sigma y j minus y bar square by sigma square, this follows chi square distribution on m plus n minus 2 degrees of freedom, and we take the ratio that will give me this as t distribution. If this is the t distribution, then this probability if I consider, probability of root mn by m plus n x bar minus y bar by s p greater than C 3, that is equal to probability of root mn by m plus n x bar minus y bar minus mu 1 minus mu 2 divided by S p greater than C 3 minus root mn by m plus n mu 1 minus mu 2 by S p. Now, this is a t distribution on m plus n minus 2 degrees of freedom. So, we are saying probability of a t variable on this is bigger than C 3 minus root m n by m plus n mu 1 minus mu 2 by S p. Now, mu 1 minus mu 2 is less than or equal to 0. Actually, if I increase mu 1 minus mu 2, then this term will decrease. If this term decreases, this probability will increase. So, this probability is increasing in mu 1 minus mu 2. So, on omega h, the maximum value will be attained at mu 1 minus mu 2 equal to 0. That is, the size condition becomes probability of root m n by m plus n x bar minus y bar by S p greater than C 3 when mu 1 is equal to mu 2. So, this means C 3 is nothing but T m plus n minus 2 alpha. You can compare it with the UMP unbiased test that we derived. This form is the same. So, in the likelihood ratio test, what is happening is that some part we are having slightly different in the one sided testing problems, but in the two sided testing problems this is exactly same as the UMP unbiased test. In the next lecture, I will derive this test, likelihood ratio test for mu 1 equal to mu 2 against mu 1 not equal to mu 2. We will also consider the testing for the equality of variances. So, sigma 1 square less than or equal to sigma 2 square, sigma 1 square is not equal to sigma 2 square. These hypothesis testing problems also I will consider in the next lecture.